Right, let's have a look at the Sn2 reaction mechanism. First thing to point out, the S here stands for substitution, the N stands for nucleophilic, and the 2 refers to the number of species involved in my rate determining step. So we'll visit those terms as we work our way through the mechanism. So what are we going to start with? Well, for the Sn2 reaction mechanism, this is preferred by primary halogenoalkanes. So in this case, I've drawn chloroethane. And why is that considered a primary halogenoalkane? Well, if I look at the carbon that's bonded to my chlorine, I can see it's bonded to just one other carbon. Now, one important thing to note in these molecules is I've got a very polar bond between a electronegative chlorine and a not very electronegative carbon. So what I might do before I start thinking about the mechanism is draw on those delta negative and delta positive symbols just to identify that polar carbon-chlorine bond. So if we now introduce our nucleophile, in this example we're going to use the hydroxide ion. Why is that a nucleophile? Well, nucleophiles are attracted to kind of nuclei or positively charged things. And what makes the hydroxide ion particularly good as a nucleophile is it's got a negative charge, so it's going to be attracted strongly to any area of positive or partially positive charge. So in this case, we've got a nice partially positive carbon, which means that probably my hydroxide ion is going to attack that carbon, and we call this a nucleophilic attack, where my lone pair on the oxygen is going to form a bond, or try and form a bond, with that carbon. Unfortunately for carbon, it can only form 4 bonds before breaking the octet rule. So as that bond begins to form, we see that my carbon-chlorine bond begins to break. And that's kind of acceptable. Chlorine's already pulling quite strongly on those electrons, which is going to kind of encourage this process to go ahead. Now you'll notice that I've drawn this primary halogenoalkane in 3D. And the reason for that is to do with how or in what direction my hydroxide ion is going to attack that central carbon. If I were to show the approximate sizes of my different groups in my halogenoalkane, I've got kind of pretty big chlorine there, fairly big CH3 group, and then 2 small hydrogens. And what that means is there's actually some kind of blocking on the right hand side of my molecule, where it's preventing my hydroxide from attacking in this direction or in this direction. So what we see happening is, as drawn on the diagram, you can see my hydroxide is attacking from the left side. And any kind of blocking of space we call steric hindrance. So in this case, that steric hindrance forces my hydroxide to attack from the opposite side of the molecule to the chlorine. Now, if I do a bit of experimentation into the rate and the things that impact the rate, I find that this first step that we've drawn so far is my rate determining step. And because there are 2 species involved, that's my hydroxide and my halogenoalkane, this mechanism, that seems a little bit strange, let's write that more clearly, is going to be considered bimolecular, because there are 2 things involved in that step. If there was just one thing, it would be unimolecular. 3 things, which is very rare, would be trimolecular. But for Sn2 reactions, that 2 is referring to the 2 molecules involved in that first step. So let's follow this process through. What I find is one bond is forming and another bond is breaking. I'm going to have a transition state where I can show in a diagram with dotted lines where the oxygen-carbon bond is forming at the same time as the carbon-chlorine bond is breaking. So this is known as a transition state because it doesn't exist like that for any length of time. We are simply moving through that transition state on the way to our products. Another important term you might come across here is the idea of inversion. So you'll notice, as we've already mentioned, that the hydroxide is always going to join my molecule from the opposite side to the chlorine. So in effect, it's kind of pushing the CH3 and the 2 hydrogens to the opposite side of the molecule to where they were before, kind of like an umbrella being blown inside out. So that process is known as inversion. Now we can draw the other side of my transition state and have a look at my products. We're going to end up, in this case, with a primary alcohol. Specifically, this would be ethanol, because it's got 2 carbons and a hydroxyl functional group. And the other thing not to forget is we've also produced a chloride ion that's now floating around in my reaction mixture as well. So because of that inversion, it means we end up with something known as a stereospecific product, which basically tells me that the kind of arrangement of my atoms around the carbon is going to be a particular way, because the hydroxide is always attacking from the opposite side of my halogen, in this case chlorine. So that's my mechanism. The last thing we might need to know about is what kind of solvent we can choose to encourage this specific reaction. And for Sn2 reactions, we tend to try and choose polar aprotic solvents. So we're looking for molecules that have a permanent dipole but are not able to form hydrogen bonds. And this kind of indicates that although they're polar, they're not as polar as things like water and ammonia. And the reason we choose those kind of solvents is because we do not want them to surround and block. If I use little yellow dots for my solvent molecules, I don't want them to be able to block that attack, nucleophilic attack, in the first step. So can we put that into words? Well, it basically means my solvent molecules do not surround the nucleophile or solvate the nucleophile, allowing it to more easily attack the carbon in that first step of my mechanism. And that's pretty much it for Sn2 reactions. Hopefully this video is of some help.